speaker is Joy Palmer from the University of Illinois Urbana-Champaign, and he will talk about lifting Torus actions to integrable systems.
Okay, great. So first of all, thanks to the organizers for organizing such a great conference and inviting me, and thanks to all the speakers for making it a great conference, and of course, happy birthday to the special birthday people here. Okay, so today I'm going to talk about sort of various questions about lifting Torus actions to integrable systems, and then I'll focus on one project I have with Sue Tolman and with Jason Liu. So, right. So throughout the talk, M omega is going to be a symplectic manifold. I'm going to assume that it's compact. Some of the things I say won't necessarily need this assumption, but let's just say it so that I'm safe. And dimension of M will be 2n. Right, so I'm interested in sort of the interplay between Hamiltonian torus actions and integrable systems. Let me quickly recall what an integrable system is. An integrable system on M omega is going to be the data of n functions from M to R. I'll usually package all these functions together into one map called the momentum map. And they have to satisfy two things. They have to Poisson commute. And they have to be somehow independent. Which just means that almost everywhere their differentials are supposed to be independent. Yes. I was just checking if anyone was paying attention, and I was the only one. Yes. So we have a bunch of functions. Together they are a map into Rn, and here's an integrable system. Right, and I'll start with an example. So a nice example of an integrable system, somehow the nicest type of integrable system, is a symplectic toric manifold. So, right, the symplectic toric manifold will have some momentum map taking M to the dual Lie algebra of the torus. In this case, if it's a symplectic toric manifold, the torus has dimension n. And so by making this identification, right, there's some choice I have to make here. I'm kind of sweeping it under the rug because 25 minutes is not very long. But you make this identification, this gives you your set of n functions. They Poisson commute, and they're linearly independent almost everywhere. I guess, I meant to make a comment, which is that this condition that they Poisson commute, the best way to sort of, one of the ways to think about why this is important, well, to me at least, is that it means that the flows of the Hamiltonian vector fields of these functions commute. And so in general, if I give you an integrable system, you get a Rn action, at least locally, but I have the word compact here, so I can really say Rn action. And a symplectic toric manifold, this is sometimes called a toric integrable system, if I'm thinking of it as an integrable system, is the one where that Rn action comes to, reduces down to a Tn action. Okay, so here is an example, I guess. And let's explain something that's been explained a few times already, which is lucky for me because I can do it very quickly. I want to say let's look at the same sort of thing, except instead of having a symplectic toric manifold where you have an n-dimensional torus acting in a Hamiltonian effective fashion, I have an n-1 dimensional torus. So like in Isabel's talk and like in several other talks. So it acts on M in a symplectic, or in a Hamiltonian and effective fashion, and you'll have some momentum map phi, which will go from M to the dual Lie algebra of this torus, which I can freely identify with Rn minus 1. And so I'm using notation just a little bit. I hope you'll forgive me. I can think of this as n-1 real functions, right? If I want to view this as somebody who really likes integrable systems, which is exactly who I am, and so that's how I want to view it, I can think of this as the data that comes with the complexity 1 space. And so now you can kind of see, well, the relationship, to me at least, between these two things, which is that if you give me a complexity 1t action, that gives you most of an integrable system. You have Poisson commuting, independent almost everywhere functions, but you just don't have enough of them. And so this sort of, I don't know, motivates a very natural question I'll call the lifting problem. So given a complexity 1 space, when can I find a function f so that, when can I find that last function? That's sort of the question. So m, omega, all of the functions that come in my complexity 1 space, plus this new function. When can we find another function that makes it an integrable system which is nice in some sense? And so I'm being vague in using the word nice because there's various definitions of nice and therefore various papers. Yeah? Well, it depends what I mean by nice. So in some cases, yes, and in many cases it is no. I mean, it's already a very interesting class at all to have an integrable system with this complexity 1 Torus section. Right, so there's some results in this direction in various cases. So the sort of parameters are what the dimension of M is and what the word nice means. Right, so the first result in this paper is very appropriate. It's one of the birthday people. This was in Yale's paper in 99, where the dimension of M is 4, and nice means toric. So Peter, as you said, you have a periodic flow. Yale Karchon has this in the same paper where she introduces the graph of a complexity 1 space. She gives necessary and sufficient conditions for when you can find that other function that makes it toric. And so now looking at this result, to me, maybe it's just because I've written it in a table like this, there's sort of two natural ways to generalize. Either I increase the dimension, or I somehow look at a broader class than just toric. So the next result in this section stays in dimension 4. I have a little music. And generalizes from toric to semi-toric, and this was by Sonia Holak, and maybe you've heard of Sylvia Sabatini, and maybe you've heard of Daniela Seppi and Margaret Symington. So 2 people who are in this room, yes, and 1 person who was in this room until a couple days ago, and then also Sonia Holak. And this was announced in 2014. They have conditions for when you can lift to a type of integrable system called semi-toric, which is a generalization of toric integrable systems. Okay, so that's one way we can generalize, right? We can keep the dimension 4 and we can look at a broader class of integrable systems. Another way you could generalize is let's look at arbitrary dimension, but keep the restriction on the system. Very nice. So let's look at toric lifting in arbitrary dimension. And this, in the case that the complexity 1 space is what's called tall, that'll be a condition here. This is a paper that I'm working on with Jason Liu, Sue Tolman, and myself. And I'll put soon for the year. Really soon, though. I think it's going to happen soon. Right, and I'll talk a little bit about the tallness condition. People have already talked about this some today. And so this is mainly the result I'm going to talk about. Today, toric lifting in arbitrary dimension. But let me put some more things on the table. Maybe you're annoyed that I said tall. It's a restriction. Can't you do it without that restriction? That would be great. So let's make another row on the table, which is if you're interested in that, you'll be very lucky. Just stay for 3 minutes after my talk. there's another talk. It'll be about exactly that. So, so Jason will talk about this after me today. And this is also soon. I don't know how soon the paper will appear, but it's in the future, but near future. Another sort of in progress thing is I have a paper that I'm working on with Sue, where we sort of generalize in both ways. So higher dimensions and more general than torque. We're looking at non-degenerate integrable systems. Integrable systems where all the points are non-degenerate. And again, we have the condition of tall. And I don't know, soonish, right? Soon, but not as soon as soon. So this is something also, right? I'm giving you guys a lot of things to look forward to in this talk. Many papers will appear in the future. And then this is another project that I'm working on with Sue. And I guess I can mention that something nice about the project I'll talk about today is that it's a key ingredient in this non-degenerate lifting. So things are all kind of linking together. And I can just quickly point out, when do I end, by the way? 45? Okay, thank you. I can point out one other paper, which is in dimension 4, and for a class of systems called hypersemitoric, which is myself with Sonia Holak. And I'll kind of put this in parentheses because it's a little bit of a different question. In that paper, we're asking the question, what's a reasonable class that you can prove all S1 spaces lift to? So instead of saying, here's a class that I like, which ones lift to this, say, okay, can I design a class that's interesting that they all lift to? Okay, so here's our history lesson that it's not really history because it goes into the future, but that's okay. So I want to talk a little bit about Yale's result, and then I want to talk a little bit about our result, and then my time will surely be gone. And so let's suppose you have a toric integrable system on a 4-manifold. My momentum map has 2 components. I'll call the components phi, comma, f to make it look like the lifting problem. So of course, the invariant of these things is the image of the momentum map, f of m. It will be a polygon. I'll draw, I don't know, the second Hirzebερg surface blown up once. It doesn't really matter. So this is slope 1/2. The other slopes, I guess, are obvious. So something you can do is you can just forget, right? The opposite of the lifting problem is the forgetting problem. If you forget the little f, no. Then you have a Hamiltonian S1 space. I have a function generating S1 action. And from Yale's classification, associated to that is a graph. And again, from this paper, well, 99% from this paper. I'm going to do exactly what's in the paper, except you have to turn your head 90 degrees, because I always draw her graphs 90 degrees of how everybody else does it. I think because I spent too much time working with semi-toric systems. Anyway, you can read right off of this graph off of this polygon, what the Carchon graph should be. Vertical walls become the fat vertices. All the other vertices become regular vertices. And edges that have non-integer slope become zk spheres. So I said that very quickly, but it's explained very clearly in Yale's paper. And I guess what you can notice, I mean, I'm talking quickly, but I think you can notice that this sort of implicitly puts some restrictions on what kind of graphs are allowed to show up. Because the features of the graph all come from the edges of the polygon. So they either come from the top or they come from the bottom. So for instance, here's a perfectly valid Carchon graph. And if you think about it for 2 minutes, you'll see there's no way that this could have come from a toric system, because one of these Z2 spheres, I guess there should be 2's on these. One of these Z2 spheres comes from the top, and another one comes from the bottom, and the other one has nowhere to come from. Right? There's no other edges on the polytope. And I guess I can say this out loud in the interest of finishing most of my talk. But this is Carchon's result, that this thing that I just described is almost, like, clearly it's necessary, but it's almost efficient. The only other restriction is that, remember, these fat vertices correspond to a fixed surface, and in order to have come from something toric, that surface should have genus 0. I mean, essentially because you don't have a Hamiltonian S1 action on a surface with some genus. And so Yale in her paper proved that these conditions are necessary and sufficient. So that is, given a Hamiltonian S1 space, if every, for me, vertical line through the interior of the graph crosses at most 2 features of the graph, and if the genus of any fixed surface is 0, that's true if and only if it lifts to something toric. So, right. Okay, so I guess I didn't forget anything. And so this is the idea that's happening in her paper. And so now I want to spend the last few minutes talking about arbitrary dimensions. And so this is my project with Sue and with Jason. So first of all, an orbit is exceptional if its stabilizer, maybe I'll just say this out loud. I really want to get to the end. I have lots of pictures I want to draw. An orbit in a complexity 1 space is exceptional if its stabilizer is larger than the nearby orbits in its fiber. So if you're thinking about S1 spaces, these are the ZK spheres. These are the, for instance, the ZK spheres are exceptional orbits, or fixed points. So I'll call the set of exceptional orbits M sub exceptional. And so other things I need to say, let's look at a complexity 1 space, M omega phi. I've used this word a few times. It's called tall if what? If whenever I take symplectic reduction by some value that's in the moment image, you always get a surface. So generically, you always get a surface anyway, but over the boundaries, you might not. I mean, actually, for instance, that toric picture I drew up there is not tall, because on the right side, if you took symplectic reduction, you would get a single point, sort of where the ceiling and the floor meet each other is the short point. And it turns out, and this is, I mean, now I'm talking about results of Karshan and Tolman. So first of all, it turns out that this surface always has the same genus, no matter which point you decide to do symplectic reduction at. And so that's an invariant of these systems. And they found a set of complete invariants, complexity 1 spaces. So Karshan and Tolman classified tall complexity 1 spaces in terms of 4 invariants, I guess. So one of them is what's called the skeleton. That's the set of exceptional points. And labeled with isotropy data as well. If you know what that means, then you'll be happy. If you don't know what it means, then I don't know. We can talk in 6 minutes when my talk is over. The genus. There's also the Dorsman-Heckman function of the action. And there's another invariant called the painting, which also people have mentioned several times in this conference. And I think I can explain kind of the ideas behind this package of invariants in one picture. And then I can draw pictures for 5 minutes. So you can look at the moment image of your complexity 1 space. It'll be some polytope, let's say, if I'm in the case where dimension of M is 6, then it'll be a polygon. You can decorate it by the image of the exceptional orbits. Right? The invariant is actually the exceptional orbits themselves, but you know, if you want to draw a picture, you can take the exceptional orbits and take their image. This is like drawing these edges for the ZK spheres. There's a genus that you just choose an integer. And there's a Dorsman-Heckman function that has to be sort of compatible with the skeleton in the right way. And there's the painting. And I just want to draw this picture. Maybe it's not a good use of my time, but that's OK. So let's suppose that the genus is 1, in which case if I take some point in the image and I look at the associated symplectic reduced space, I should get something which is homeomorphic to a torus. And I say homeomorphic because if you're at an exceptional orbit and you do this reduction, there'll be some sort of singular point. So there's a point like this. And in this case, so I drew this nice picture. This is from, the picture is exactly from their paper. If I walked in sort of a circle, at each point, as I go along that circle, the singular point will sit somewhere on this reduced space. It'll go on a little journey. It'll do whatever. And it might trace out a non-trivial loop. And so this gives you some flavor of how the painting invariant is gonna measure how these things twist. But I should warn you that this is really just like a flavor. The painting it's defined in a little bit of a different way. This doesn't exactly capture the entire behavior, but it kind of gives you the idea, I think. Okay, I'm gonna have to talk very quickly. Let me erase what I just drew. So I want to try and draw that picture. So say I have a 6-dimensional manifold. Phi is 2 functions, and then little f is a single function. Its image will be some Delzant polytope. Here I'll choose the sphere with sort of a cut off of the edge. Here's a good chance to give some intuition for the word tall. The complexity one space being tall has to do with the ceiling and the floor of this thing not touching each other. And if I forget about f, I get a complexity one space, and the invariance of it can come from projecting this down. You look at the projection of this thing, it's just sort of its shadow, and this edge that lies over the interior becomes a part of the skeleton. So you can just read the underlying complexity one space off of the Delzant polytope. And so now I can very quickly explain that, that I can draw some pictures, I guess. So the idea is that if I give you a complexity one space whose skeleton looks like this, certainly I can lift it. I put sort of a bend on the top. And if the skeleton looks like this, that's also fine. I put a bend on the top and I put a bend on the bottom. And if the skeleton looks like this, there's no way I can lift it, right? So I'm trying to explain this in a way that's completely analogous to what Yale did, right? Because one of these bends is going to have to live on the top, one has to live on the bottom, and the other one doesn't have anywhere to go. And so if you think about this for a bit, you will maybe come up with a conjecture. I've essentially argued half of it. I can make another comment in 45 seconds. I gave sort of a vague argument for why Cauchon's theorem should hold, but not really. I mean, I didn't write it, but I only gave one direction. The other direction is sort of the harder direction. And I'm doing the same thing here. You can see that this one doesn't lift, but it's not totally clear that any skeleton that can be split into 2 pieces can lift. But if you wanted to guess that, you would not be wrong. So hidden here is a surprise, which is our theorem. So with Sue and Jason, I think it's fair to call, I mean, it doesn't exist written down yet, but it really will be soon. So a tall complexity one space can be lifted to a toric system if and only if the skeleton is 2 colorable, which you can guess what this means. It can be split into 2 pieces such that the moment map is injective on each of those pieces. Sort of you can lift one to the top and one to the bottom. The genus has to equal 0. So that means if I take the symplectic reduction at any level, in principle it can be any integer, but I require it to be 0 if I want to lift to something toric. And the painting is trivial. And this sort of has to do with the fact that if you look at a toric system, you have stuff going on the top and you have stuff going on at the bottom, and they're not going to twist around each other. This is, I don't know, I'm proving lots of pages of math in very few sentences. But yeah, it turns out to be an if and only if condition. And the difficulty, I'm going slightly over, the difficulty is not in, if I have some skeleton, lifting a single vertex is not hard, and lifting a vertex that's next to it in a compatible way, right? You want to lift them so that they kind of glue together, is not so hard. But as soon as you have two different conditions on the same vertex, things become much more difficult, but you can do it. And I will say, you will learn how to remove the word tall from this, from Jason, and with Sue, we're working on changing toric to non-degenerate. So, okay, sorry for going a little over.